So this relation between multi-value functions turns out to be true. So to show this, let's look at what the left-hand side gives us. So we've got log of, and then we'll write our z as r to the I, v to p as normal. It's raised to the power 1 over n. So we take the nth root of r, and we've got e to the I v to p plus 2 pi m and then all of this divided by n. So what does that give us? Well, if we take logs of this, then we get 1 over n, just the ordinary log of r, plus I v to p, all this divided by n, plus, because we're taking logs, we can always have an extra, we can always add an extra 2 pi I times an integer. So we'll just write that down there. If you like, we could have put that here, another plus 2 pi I p. So all of these things, n is an integer, m is an integer, p is an integer. I should really do things a bit more carefully. So I think we're talking about n as a positive integer. And m is any number from 0 up to n minus 1. Okay, so now let's look at the right-hand side. What does that give us? So 1 over n log z is, again, 1 over n log of r plus, and then z I'm going to write as r times e to the I v to p, which when I take logs I just bring that down. So I've got where, okay, q is any integer. So the question is, are these two things, is there a one-to-one correspondence between these two quantities? Obviously the 1 over n log r is the same in both cases, but for any allowable value of m and n and p, can we find the appropriate value of q? And basically the answer is yes, because what have we got? We've got any number over n, any integer over n as a multiple of 2 pi, which we can get from adding m and p, and basically q can be any integer, and we're defining it by n. So in fact these two things, although they look a bit different, we can always choose a q which matches any m and p that we choose. So those two things are indeed equal.